on uniform continuity. First, we're going to define it. Definition. Okay, the function is continuous. At point A, where x is a, if first condition, the point A is in an open interval, is in an open interval. Okay, so that's the first open interval I. So we're going to, anytime we see I, that we're classifying that as interval. Contained in domain, we'll call our domain D. And the second condition minus f of a. Not using the limit, we're comparing 2 points. Less than epsilon whenever x minus a is less than delta. Okay, so if our function f excuse me, is continuous at each point of a set, and we'll call that set S. Then we can say that our function f is continuous. If is continuous, it's continuous on set S. Okay, and also a function is said to be continuous, if it is continuous at every point of its domain. Okay, nothing new there. So basically, here we have a graph. Okay, and we'll show that it's continuous, and here's point A. These different, here's red. Here's point A, okay, and that is going to be f of A. Of course, that'll be our limit. Then we have here A plus delta. If this is some value delta, then this will be A plus delta, and this is some value delta, same value, same delta, then this would be A minus delta. So this would be f of a minus epsilon. This would be f of a plus epsilon. Okay. So, and of course, this value here is epsilon. This is the same value epsilon. It's not drawn to scale, but these two epsilons should be the same value. All right. So we're saying here that the function f is continuous at a here if the point A is in an open interval I. Okay, we have an open interval. So this open interval would be a minus delta to a plus delta. Okay, so that's our open interval. I is our interval. Okay, our interval is continuous, is contained in domain D, and for all epsilon greater than 0, there's a delta greater than 0, such that, so this would be, so some value x, right? This would be, if this is x, this would be f of x. So we're saying f of x minus, or f of x minus f of a is less than some value epsilon. So we're talking about anywhere else besides a on this interval. Whenever x minus a is less than delta. So if this were x and this were a, then x minus a would be less than some value delta. Okay. If f is continuous at each point, so we're talking about all points maintaining continuity for set A, then set S, we say that our function f is continuous on set S. So all the points that we're referring to are all within set S. A function is said to be continuous if it is continuous at every point on a domain. Okay, so that's what we have so far. So that's continuity, okay? It's continuous. So we've just kind of reviewed continuity. Now let's look at uniform continuity. Okay, so uniformly continuous. So uniform continuous is, here we have a function f with domain S is said to be uniformly continuous. Uniformly continuous on set S if all epsilon greater than 0, there exists a delta greater than 0, such that for f of x 1 minus f of x 2 is, the absolute value of that is less than epsilon. Now before, on the other one, we used f of x and f of a. So f of x1, f of x2, f of x, f of a, you know, it's basically the same thing. Whenever we have the difference in x1 minus x2 is less than delta. Okay, so instead of f of x and f of a and x minus a, we used f of x1 and f of x2, f of x1 minus f of x2. Okay, so as long as these two match. Okay, and x1 and x2 are elements in set S. In the last problem, we would have put X and A are elements in set S. Okay, so the important condition of uniform continuity states the same value for delta holds for all x1 and x2 that are, of course, elements in set S. Okay, so let's see what this looks like graphically. All right, so now we start off really steep. I can still do that. Okay, so no, let's redraw that. It didn't come out quite the way I wanted it to. So all right, so it still didn't come out right. All right, let's try this again. This time I'll draw the curve first. That's better. Okay, and here we have and epsilon is somewhere between here and here. So this would give us a delta, this would give us an x1 and an x2. So this is delta. So now if we look further on down, like about here, here's the same epsilon, but let me use that in green this time. And let's see, this goes down to here. And so now we have an x1 and an x2, but our delta is much different. You can't see that green real well. Here's x1 and x2, and then the other one. So here the delta is much larger than the other one, so therefore we do not have uniform continuity because the deltas are different between x1 and x2 in one place in comparison to epsilon. Epsilon's the same here at the top, and you can see the delta x1 and x2, that's our delta, but when we come further down the line and we use the same epsilon, the delta is not the same, so therefore this function is not uniformly continuous. So we would say here that here the function is continuous, but not uniformly continuous, but not uniformly continuous. The same value for delta does not hold for all x1 and x2 that are in set S. The steeper the function, the smaller the delta is required. So that is uniformly continuous, where basically the slope would basically have to be the same throughout the curve within that domain. So that concludes this video.